Hello, my name is Eitan Rosenfeld, and today I'll be introducing RAIDP, a distributed storage solution for warm data. The sheer scale in today's data centers means that there might be hundreds of thousands of disks. Consequently, disk failures are a common occurrence. So to prevent data loss, redundancy comes in two forms, either replication or erasure coding, but these schemes have trade-offs. Replication consists of making one or more copies of the data to other disks. Recovering from a disk failure is fast. Just make a copy of a surviving replica. The alternative is erasure coding, where the data blocks are processed to create one or more parity blocks that can be used to reconstruct the data after a failure. Notice that for every additional parity block, the entire set of data blocks in a stripe is resilient to an additional failure. Erasure coding is therefore far more efficient in terms of storage capacity than replication. And yet, most storage systems use triple replication for their warm data because replication parallelizes accesses to data and avoids costly encoding overheads. But one of the biggest reasons is improved recovery. Recovery is better with replication because you only need to replicate exactly what was lost after a failure to other disks in the system. With erasure coding, reconstructing a lost disk means reading data blocks from every affected parity stripe throughout the system. But unfortunately, replication is expensive. So replication is only used for warm data, and erasure coding is used for the rest. With these trade-offs in mind, our goal is to quickly recover from two simultaneous disk failures without resorting to a third replica for warm data. This goal inspired RAIDP, a hybrid distributed storage system that seeks to minimize the disadvantages of both replication and erasure coding. RAIDP stores only two replicas of each data object, yet it can still survive two simultaneous disk failures. We'll demonstrate this failure tolerance with how data is carefully laid out. Disks are partitioned into multi-gigabyte sections called superchunks. Here we have 5 disks with 4 superchunks each. We will lay out the data such that it meets two criteria: one mirroring, where every superchunk is two-way replicated, and one sharing, where two disks share at most one superchunk. Together, these two properties mean that a failure of any one disk results in a simple replicated recovery, and a failure of any two disks will only result in at most one lost superchunk. Let's see this in action in a sample 5-disk system. Here, we also introduce a new piece of hardware imagined for this system, a local disk add-on that is attached directly to each disk that interposes the I/O to the disk. This disk add-on has exactly enough storage to store an erasure code of the disk's superchunks, and we store the XOR of the disk's superchunks on it. In this illustration, when the two disks fail, superchunk 2 is lost. But now we can use the disk add-on on one of the failed disks, in this case disk 1, in tandem with surviving superchunk copies from disk 1, in order to recover that one lost superchunk. We simply XOR the data on the add-on with the data from disk 1's superchunk mirrors. By doing so, we are able to recover superchunk 2. Note that we could also recover the lost superchunk using the add-on from the other failed disk and its set of superchunk mirrors. We implemented RAIDP in Hadoop with a 3,000-line patch that simulates the disk add-ons in memory. We evaluated our implementation on a 16-node cluster with 6 GB superchunks for an effective capacity of about 800 gigabytes. We compared RAIDP to triple replicated HDFS using standard HDFS benchmarks. We'll focus on the writing benchmark, where we test the runtime of writing 100 gigabytes in a cluster. In the leftmost graph, the y-axis shows the runtime. We see that RAIDP is 22% faster than triple replicated HDFS because RAIDP performs significantly less I/O because it writes only 2 replicas. The graph on the right shows the network usage of the writing benchmark. The y-axis shows the network usage in gigabytes. RAIDP uses half the traffic that HDFS with 3 replicas does because RAIDP makes only one additional copy of the data instead of 2. Finally, we measured recovery time for RAIDP versus RAID 6 erasure coding. Both with a 1 and 10 gigabit per second network, RAIDP recovers 14 times faster than erasure coding. And remember that with erasure coding, such a recovery is required for every disk failure, whereas for RAIDP, such a recovery is only required for one superchunk upon a second failure. To sum up, RAIDP offers storage, write performance, and network efficiency improvements versus triple replication, and offers quicker recovery than erasure coding. We hope it can open the door for storage providers to move from 3 replicas to 2.